Welcome everyone. This is webinar 3 of the series in preparation to the second International BioHackathon of the Bioinformatics Italian Society 2020 that is going to be held before the BITS conference in Padova. So this webinar is about the inference of gene regulatory networks and evaluation metrics. I am Antonio Collesei, a researcher at the Veneto Institute of Oncology, and I will take care of the first part of this webinar. So, where we left off. In the first webinar, we actually talked about more the biology side with regulation and transcription factors, while the second webinar, the one from last week, was about the creation of the count matrix from FASTQ files. Then we also understood how to explore the data with principal component analysis and clustering. And today we're going to talk about, given a count matrix, how do we actually infer a regulatory network. So this is what we are presented with. So an expression matrix with genes and some samples and the relative expression values. What we want is a network, a series of links between these genes that actually tell us how the genes are related to each other. The roadmap for this presentation will be, we start with correlation and mutual information techniques, then we go on with some causality methods, even though we will only talk about approximations, linear regression, and then partial correlations, Gaussian graphical models, and in the end, metrics to evaluate if our model is actually performing well. So let's start with correlation techniques and mutual information. Correlation is a pretty straightforward metric, and it's a measure that expresses how well two variables are linearly related. So if they change together, then they are correlated. For example, in this case, we see gene B and gene C that are actually growing together at the same rate, so they are perfectly correlated. Of course, this is just a stupid example. But in the end, what we will have is a perfect correlation link between gene B and gene C. So the edge is weighted more, is stronger than the other ones because the correlation is stronger. There are various types of correlation. We will only talk about two. For example, Pearson correlation assumes normality in the data distribution. So of course it goes well with data that are normal, that are normally distributed. And informally we can say that this couple of genes show similar expression patterns across different samples, and so they are linearly correlated. But for example, if we have different data, we may be looking at Spearman correlation that uses ranks of expressions instead of raw data to measure this relationship between genes. And of course, if there is a high Spearman correlation, then you are looking at a couple of genes or groups of genes that increase or decrease together monotonically. So the method of choice for this kind of analysis that takes correlation as the basis is WGCNA, which is weighted gene co-expression network analysis. You will see here in the bottom a link if you want to follow through the vignette. And it's a method that identifies clusters that are groups of genes that are highly correlated to each other. And also you can find hub genes, so the actual drivers of these groups of strong links of correlation between each other. And so if you look at the left of the image, you will see what we found before. So stronger links mean higher correlation values. But correlation has some pros and cons, mostly cons, because even though if it is fast to run, interpretable, and a good starting point, you are only looking at linear relationships, and usually biology is way more complicated than this. And also you have to account for potential spurious links. So in order to try to avoid these cons of purely correlational approaches, you can try to go on and use mutual information, for example. So this is why regulatory interactions are not usually linear, so correlation doesn't really work well. So you can try to infer some kind of statistical dependencies between random variables. So in our case, genes. So this is the formula of mutual information, and essentially it captures the uncertainty. So not really the correlation, but the uncertainty, the entropy of a certain variable, in this case A, minus the uncertainty on A given that we observe B. It's symmetrical as a measure, so if you look at the entropy of B minus the entropy of B given A, then you have the same exact value. But let's look at an example just to understand better, because this formula is a bit not really explainable in a sense. But we can informally try to understand it from this example. So imagine you have these two variables. One is rain and the other one is people with umbrellas. And imagine you are inside a room, a dark room with all the windows and the doors closed, and you cannot look outside. And you're wondering how many people are there outside hanging with their umbrellas. And you have a high uncertainty on B. But if you open the window and you look outside and you know that it's raining, then you have better knowledge on B and the uncertainty goes down. So in this way, there is high mutual information between these two variables because one reduces the uncertainty of the other. So at the same level, you can try to find relationships between genes. So maybe knowing that one gene is always on, then it means that the other one is always off. In this way, you can find these statistical dependencies between variables, even though still there is the caveat that the links are not directional because we are not looking at causality. And the method of choice is Arachne. Again, you can find a vignette down below with some better explanations if you are interested in this. But Arachne actually uses mutual information to find relationships between gene pairs and build regulatory networks. As a plus, it has a pruning step that uses the data processing inequality to try to limit the inference of weak or less likely edges and produce a cleaner output result. Still, mutual information is not perfect because you are producing, as we said, undirected networks. And also it is computationally more demanding than just purely correlational approaches. But the actual pro is that you're looking at non-linear relationships, and it's also in line with biological principles and assumptions. But let's see if we can do a bit more, because the actual final step would be purely causal models. But they are difficult to achieve because they need a lot of data, a lot of computing power. So we are not really looking at purely causal models because for this webinar series it goes a bit out of context in order to prepare you for the contest at the end of May. So let's try to understand what is causality and what we can do kind of easily in this contest. So imagine that you have 20k genes. This means that you have 200 million gene pairs. And even if we assume a 5% confidence, then we can expect 10 million false positives, which is a lot. And this is brought by chance alone. And this is why there are spurious links that can happen between genes because they are both generated from a mysterious generator. So confounders, whatever confounder, drugs, circumstances, or another gene. And so these genes appear related, but they are actually not. So in order to reduce this uncertainty on the relationship between genes, we can try to use some other tools. And we will see a tool, which is Granger causality. But first, let's see what actually is a spurious association. This is an example from a pretty famous website that tries to collect all the weirdest correlations in history. For example, in this case, the popularity of the first name Stevie is actually correlated perfectly with the stock price of Netflix. And they are actually not related at all, but still they correlate a lot. So we need to try to avoid this kind of spurious correlations. And because causality actually is different than correlation, because if gene A changes in expression, then gene B changes too. And it's not that you measure like a variation that goes together hand in hand. Also, causality gives you an asymmetric relation, so you can say that one gene is actually causing the other ones. The only problem is that usually you need specific data, for example, knockout experiments, but we can approximate this with Granger causality. And Granger causality actually needs time series data because we can say that gene A Granger causes gene B if looking at past values of gene A actually improve the prediction of values of gene B. This is actually looking at preserved patterns over time of a certain gene with another one. So if we look at this image, we see that there is this similar set of patterns that happen in gene B a little bit later than gene A. So in this case, we can say that gene A Granger causes gene B. It's not perfect, it's not an actual causality per se, but it's a bit more than correlation and mutual information. So it has a lot of pros, which is giving directional edges. It's a bit more grounded in statistical hypothesis testing, and also it's the best approach for perturbation time series, which is what we saw in webinar 2, sorry. So if we haven't looked at it, you can find it in the YouTube channel. Which is that, of course, you require a specific type of data, which is time series, and it's not really scalable in terms of processing power for thousands of genes. And also, it doesn't have a direct explanation in biology because you're not looking at pure causes, but you're looking at an empowered correlation. So still there is room to improve. And that's why we are ending part 1 and we will be going on with Elisabetta to another set of techniques in order to tackle these kind of problems. So I leave the word to Elisabetta.
Hi everyone, and welcome to the second part of today's webinar. I'm Elisabetta Sciacca, researcher at Humanitas University. In the first part of this webinar, you explored how variables move together through correlation, mutual information, and some approximation of causality. But knowing that two variables are related is just a part of the story. The next step now will be about going further and see whether we can model this relationship, and if so, in which direction. So this is exactly where linear regression comes in. In fact, linear regression is a statistical method to model the relationship between a dependent variable and one or more independent variables, using the equation of a line. So while correlation is symmetric by nature, that is, it will tell you that x and y are related to each other, but it will say nothing about who drives whom, regression introduces that element of directionality. So we will have predictors on one side and the outcome variable on the other side. So in our scenario where we want to predict gene regulatory networks, our response variable y will be maybe the expression of a target gene A, and our predictor variables might be represented by transcription factors or upstream genes that are putative regulators of that gene A. A few assumptions before we move forward. There are a couple of things that must always be satisfied if we work within the framework of linear regression. First of all, linearity between x and y, independence between variables, homoscedasticity, and normality. Just a note, do remember that if you work with raw RNA-seq counts, they are usually not normally distributed. So if you want to apply any linear regression, you will have to transform your data first. So apply log2 or some sort of variance stabilizing transformation that will make your data normally distributed. So as I said before, in the context of inferring links between genes, the most simple model we can think of is just the one that will predict the expression of a certain gene A as a function of the expression of a gene B. And our goal will be to find the best line that fits better the data. So let's break down this equation. Beta 0 will be our intercept, so the basal value of gene A, the value of gene A when gene B is 0, is off. Beta 1 will be the slope coefficients, let's say, so how much gene A increases for each unit increase of the expression level of gene B. And epsilon will be the error, so the difference between the predicted and the observed value. So it might be some sort of biological variation that gene B alone is not explaining. It might be due to a nonlinear regulatory dynamic or measurement noise. So it's the part of gene A's expression that our model couldn't really account for. So it's clear that it's something we need to measure and to quantify to understand how good our model will be. That is why we introduced the concept of residuals. So for each data point, the residual is just the gap between what the model predicted and what was actually measured. So the smaller those gaps, the better our model fits the data, of course. And we can summarize this with a number, a single number that is called R squared, and represents the proportion of the variance of gene A's expression that is actually explained by gene B. So R squared of 0.81, for example, means that the 81% of gene A variability is explained by gene B. Now, in reality, most biological processes depend on more than one factor. So a more realistic model would include all relevant factors you need. So for example, we would have to account also for another gene in the expression of our gene A. And how we would do this in R? The simplest way, and let's say the most common way, is just to use the LM function. That is pretty straightforward. You just input your regression function and your data, and what you get is a result similar to this one, where there are key things to look at. Of course, you want to look at the coefficients. So in this case, for example, the intercept is 2.4. So when both the expression of gene B and gene C are equal to 0, let's say they are off, the basal expression of gene A will be 2.4, for example. While the coefficients of a beta 1 coefficient of 3.2 for the gene B expression means that we predict that every time the gene B expression level increments by 1, then the expression of gene A will increase by 3.2 units. And this just holding the gene C constant, no, not varying gene C. And same, of course, will be for this coefficient here. Another column that is telling that is quite important to look at is the p-value column, because it's telling us the statistical significance of each predictor in our model. So it will tell the p-value associated with the t-statistic of each coefficient. And finally, there's the R squared, that is the proportion of variance explained by our model. So we know we want small residual, but how does the model actually find this best line and the beta coefficients for having small residual? Basically, the function that it used is the loss function, the so-called loss function. And it works by finding the beta coefficient that minimize the errors and the residuals. This function is called specifically sum of squared errors, and we'll try to minimize all those gaps here. Now, this works quite well as soon as you have few predictors, sorry. But if we want to infer, let's say we want to infer here gene regulatory networks, so if we want to do this from transcriptomic data, it means that for each gene, we want to identify which other genes are influencing or, let's say, regulating it. So in practice, that means that gene A could potentially be predicted by every other gene in the dataset, and we want to explore this and to understand which are the genes and how much they influence our gene A. So this means we have hundreds of candidates for gene A. So in this type of setting, the standard loss function becomes problematic, because it will try to use every single gene to explain the outcome, and it will assign a non-zero, even a small weight for all of them. So it will capture a lot of noise from our data and less biology. So how do we force the model to be more selective? The strategy that we can use is to penalize it for being too generous with its coefficients. So this is the idea behind the L1 penalty and the lasso algorithm. We add a term to the loss function that pushes the coefficients towards 0. And this will be this term. So now, if this is our new loss function, the algorithm must now balance two goals: fitting the data and keeping the sum of the coefficients as small as possible. So this means that L1 forces the coefficients that are noisy to become exactly 0. So, to sum up, with linear regression and lasso, we found a way to model the relationship between genes and identify putative regulators. Now, let's move on to the next step of our journey and to partial correlations. The question is simple. Once we've found that two genes are related to each other, how do we know that this relationship is direct? That is, are B and C correlated to each other because they happen to be regulated by another gene A, or just because their relationship is direct? This is exactly what partial correlation is meant to do. Partial correlation measures the direct association between the two variables just by removing the shared variance of all the other genes. So if we find that partial correlation is zero, then we can be sure that the two genes are conditionally independent. Finding conditional independence one by one across thousands of genes would be computationally unfeasible and also mathematically unstable. So Gaussian graphical models are introduced to give a probabilistic framework to infer undirected graphs based on partial correlations. How does it work? First of all, we need to make another assumption again. That is that the continuous gene expression data must follow a multivariate normal Gaussian distribution. So again, if you work with raw RNA-seq data, you will have to transform your data again to make it normal. Now, assuming a multivariate Gaussian distribution means treating the expression level of all genes in our dataset as a single random vector. Now, until now, we spoke about single genes, and therefore we were talking about univariate Gaussians. Now, if a univariate Gaussian is described by the single mean value and the single variance, the multivariate Gaussian will be simply described by a vector of mean and a covariance matrix. The covariance matrix will give us the variance of each individual gene in the diagonal, but crucially will also give us all how each gene covaries with all the others. And that's crucial, of course. The covariance matrix contains, this way, all the simple correlations, so all the marginal dependencies, and the precision matrix, that is the inverse of the covariance matrix, mathematically removes all the indirect paths and will leave only the partial correlations. So if the covariance matrix was representing our dense and full network with a lot of spurious and indirect effects, the precision matrix will actually tell us the real network. So to intuitively understand how it's happening, we must go back to the single representation of a gene-gene link through linear regression that we were describing before. So mathematically, the simple regression we had was just this one. And the way to find the coefficient, the beta coefficient for this regression was just to find the covariance scaled by the variance of the predictor. So, however, this part here, this covariance, is telling nothing about the effect of other genes. So even if gene A and gene B vary together because of the stimulation of a gene C, the covariance of gene A and B will still be high. So beta will be high, and the link will be drawn in our network if we follow this method. So now when we work with all genes together, we go to algebra, and the algebraic equivalent of the covariance of gene A and gene B is the covariance matrix, which contains all the marginal dependencies. Now, to model the effect of gene A and gene B net of all the other genes, we need, as we said, to regress out the effect of all the other genes by adding them as predictors. So we need to build something like this, as we were saying before. Now, the equivalence in algebra would be to solve a multiple regression and would mean, in this case, to invert the covariance matrix. That means the precision matrix. So all the elements of the precision matrix perfectly encode these multiple regression coefficients. Now, we still have another problem. With omics data like RNA sequencing, usually we measure thousands of genes. like 20,000, for example. And we only have, if we're lucky, 50 to 100 of samples. So the number of predictors is higher and way more higher often than the number of samples, which means that covariance matrix is not invertible. So we cannot compute the precision matrix directly. However, what we also know from biology is that gene regulatory networks are sparse because most genes, they do not interact with each other. So how do we handle this? Again, we force sparsity and we use again L1 penalty. So if in the single gene scenario we take the L1 penalty and we apply it to the estimation of the entire network, in this scenario we use G-lasso, which is the equivalent of this context. Instead of just finding the inverse covariance, G-lasso estimates the precision matrix by penalizing the absolute size of each of diagonal elements, which means this regularization stabilizes the calculation and will allow us to calculate the precision matrix even in the scenario where the number of predictors is less than the number of samples. So we obtain a sparse precision matrix, and the remaining non-zero elements that are present in it represent the real strong direct regulatory interactions. So with this, we covered all the key methods we needed to infer a gene regulatory network from our data. So we will now move to the next and last section of this webinar, which is about evaluating the goodness of the network we predict. Let's say we predicted a network and we want to know if it actually reflects biological reality. So to do this, we want to compare our statistical associations with the gold standard, which for us is, let's say, a reference network built from validated biological experiments. To compare the inferred network against the ground truth network, we must start from the so-called confusion matrix. This is just a table where we compare the true biological presence or absence of links with what we predict. So basically in this table we just write numbers, that we write the number of true positives, so all the links that were predicted by our network successfully because they were also matching a biological relationship, a real one. False positives are those links that were predicted but were not observed in reality. False negatives are links that were not detected by our network, but they actually exist in biology, while true negatives are those absence of links that actually do not exist in reality. So true and false positive and negatives are used to calculate several metrics. The first we can start with is, of course, accuracy. It is the proportion of all classifications that were correct, whether positive or negative. So mathematically is defined as the ratio between the current classifications, so the sum of true positive and true negatives, and all the total of possible classifications. So a perfect model would have 0 false positives, 0 false negatives, and an accuracy of 1, let's say 100%. So it's usually the default metric evaluation because given a balanced dataset, accuracy looks like the best measure of model quality, of course. However, if the dataset is imbalanced, or where there's a kind of mistake that, let's say, the false negative or the false positive that is more costly, and this happens often in real case scenarios, it might be better to optimize for other metrics. Let's see a few considerations for our scenario. So we have a number of nodes of our network, so the number of genes, that is huge. And the possible connection between these genes will be n squared, so it will be a very big number. However, we also know that the vast majority of possible genes do not exist in reality. We know that just a single transcription factor only regulates a very small fraction of the genome. So this creates an extreme class imbalance because the number of true negatives, so that the edges that correctly do not exist, is enormous compared to the number of actual biological interactions. So this sparsity tells us which evaluation metrics we should trust and we should not. Let's think about accuracy, for example, in this context. If a gene regulatory network contains only 1% of true links among all possible links, a model that is predicting no link, absence of link every time, will get 99% of accuracy. But it's completely useless because it's not helping us in predicting anything. So let's introduce another type of metrics that is recalled, is also known as sensitivity or true positive rate, which is the proportion of all actual positives that were classified correctly as positives. It's also defined mathematically as the ratio between the correctly classified actual positive and all actual positives. So it's answering the question, what fraction of real biological links are detected by my model? And an hypothetical perfect model would have 0 false negatives and therefore a recall of 1, so 100% detection rate. While the false positive rate is the proportion of all actual negatives that were classified incorrectly as positives. This is also known as the probability of false alarm, and that's the mathematical definition. And it answers the question, how many actual negatives were misclassified? So a perfect model would have 0 false positives and therefore an FPR of 0, so 0% false alarm rate. So in an imbalanced dataset, this false positive rate that we can also call specificity in some scenario is generally more informative than accuracy. However, if the number of actual negatives is very low, the false positive rate might not be the ideal choice. For example, if there are only 4 actual negatives in a dataset, just one misclassification will result in an FPR of 25%, while in a second misclassification will cause us an FPR to jump to 50%. So in cases like this, maybe precision that we are going to describe will be a more stable metric. Precision is actually the proportion of all the model's positive classifications that are actually positive. It is mathematically defined as the ratio between the correctly classified positives and the sum of the true positive and the false positives. In our scenario, it will represent the number of predicted links that correspond to actual biological relationships. So, precision improves as false positives decrease. Recall improves when false negatives decrease. Another metric we could use is F1 score, which is the harmonic mean of precision and recall. This is the mathematical definition, and when precision and recall both have perfect scores, F1 will also have a perfect score of 1. But if they are close in value, F1 will be close to their value. But if they are far apart, F1 will be similar to whichever metric is worse. That's why F1 score is quite useful. There's also something else to think of. Actually, our algorithms rarely output a binary answer, let's say yes or no, edge or not edge. They usually output a continuous value, like mutual information or regression weights, as we discussed. So instead of picking an arbitrary threshold that it will tell us this is an edge and this is absence of edge, we can also calculate our metrics at every possible threshold that we could have. And we can do this approach is used by two different strategies, the AUROC curve and the AUPR curve. Let's see what they are. The receiver operating characteristic curve is the visual representation of model performance across all thresholds. So the ROC curve here that we find here is calculated by the true positive rate and the false positive rate at every possible threshold. And then we just plot TPR over FPR. So a perfect model will have an area under the curve of 1, like in this case. So this AUROC, this area there is under this curve, indicates how accurate the model is at ranking positive cases above negative cases at all possible thresholds. So in other words, it is measuring how well the model is good at catching true positives without having too many false positives. So the x-axis is the false positive rate, while the y-axis is the recall, so the true positive rate. The diagonal line will be the random classifier. So the closer this curve go to the diagonal line, the worse, because it's like it's not predicting anything. While the better the model will be, the closer it will go towards the top left corner. This red point here, for example, is telling me that a certain threshold, the model correctly classifies 84 of the true positives and misclassifies 10% of actual negatives as positives. While the area under the precision recall curve measures how well the model balances between precision and recall across all thresholds. So in other words, in this case, we're measuring how well the model is good at catching the true positives without having too many false positives. The x-axis of this plot is recall, while the y-axis is precision. This dashed line is the baseline precision, which corresponds to the positive class prevalence. This curve will be the higher the better, let's say. And in this example here of this red dot, it means that for this particular threshold, my model is correctly identifying 60% of all actual positives and 55% of classified positives are actually positive. So a few considerations at the end, just to compare the two. While the AUROC is giving me a plot where we have sensitivity versus 1 minus specificity, the AUPR curve plots recall versus precision. So AUROC is generally robust, but can give a high score if the number of negative samples is very large. Even if the model performs poorly, we will see a very good curve. While because precision depends on the number of false positives, relative to the total of predictive positives, it is more effective when the positive class is rare, like, let's say, in our gene regulatory networks. So while AUC-ROC curve is better for general purpose classification where the classes are roughly balanced, the AUPR curve is surely better for rare events and better for our type of scenario. So that was everything for this webinar. I'll leave you here a few references and useful links about this last part of the matrix evaluation. And I thank you for joining us, for taking part of this biohackathon, and for all your attention.